And basically I'm just going to do essentially what we did with the handheld version, just now that it's on the robot.
Today we are looking at the Frontier device. It has an embedded computer, a multi-camera system, a LIDAR, and inside there is hidden an inertial measurement unit. The cameras work pretty much as our eyes. The LIDAR basically allows you to get a point cloud of the environment by firing lasers at the environment, and by measuring the return time, it can get you a metric measurement of what's around you. And the IMU works pretty much as our internal ear. It gives us an idea of where gravity is and how fast we are rotating. All of these sensors can be fused together to answer the main question in robotics called SLAM, Simultaneous Localization and Mapping. So the localization bit is knowing where you are, and mapping is what's around you. SLAM is pretty much like a chicken egg problem. You don't know where you are, you want to know where you are in the environment, but at the same time you also want to know how the environment looks like. If you walk around, you're gonna see an orange line that shows where we were before. So if I keep walking around and I come back to the same place I was before, I can show you the main ingredient of SLAM, which is loop closure. There you go. So here you see a red line. This red line means that the system who recorded all of our previous position recognized if we were back to the same place. And in this way, we can correct all of the error we have accumulated this far and have a better map by adjusting it, knowing that we were there before. The screen was just to quick visualization, but all of the problem is being solved in 3D. So here is the exact same problem we have solved before. So here you see the table, we see all of the map in 3D being built, and the loop closer is right here. So after just a very quick walk, we have a complete 3D map of the environment, and we also have our past trajectory. The map is mainly built using the LIDAR because it gives you a continuous stream of point clouds. But to accurately know where we were, we also need to fuse the IMU because there is physics inside. So the IMU tells us your acceleration, for instance.
So IMU is like
inertial measurement unit, yes. If, for instance, there is an error of registration between 2 point clouds and we don't use the IMU, the system might just think we teleported somewhere else. But the IMU is telling us, no, your acceleration was like that, so your velocity should have been like that, and you should be here instead of somewhere else.
So if you use the IMU on its own, it'd be kind of dead reckoning. It would be guessing a rough idea.
Yes, so there is a component of dead reckoning, but this is fused together with the other sensors. So if we were doing dead reckoning all of the time, then we would end up on the moon because there are many smaller errors that gets integrated over time. So the IMU is just giving us an idea of where we should be between two camera images or between two LIDAR point clouds. And then the measurement from the point clouds and the cameras kind of correct those and are merged together. So we can have a walk and go downstairs in the lab. So we unofficially call it the Bat Lab, and the reason for that is because we have a huge elevator that can carry an entire car. Here we are going to show the quadruped section of our lab.
What's funny is the camera can see some of the LIDAR.
Yeah. Yes, because it's near infrared, and camera don't have infrared filters. There you go. So here we have different quadrupeds. Today we're gonna see the spot one. This is all the way from where we were before here with the round table, the loop closures, and we went downstairs. So all of the computation is inside here, but for ease of visualization, we have some interfaces on the phone and on the computer. And most of our software is compatible with ROS, which is a framework that is widely used in robotics community. There are many libraries and programs ready to use to accelerate robotics. This one in particular is called ROS board, and it's running a little server on the computer. And on the other side, there is a client that gets the outputs from our algorithms as messages, and these messages are then relayed and visualized in the web page, web browser interface.
So on the phone, that's just basically running.
Yeah, I mean the phone is it's just an optional that we use, especially when we do handheld missions. We want to have an immediate feedback of what's going on, everything is going all right, so we have developed this interface.
SLAM is very useful for robotics in particular because it allows us obviously to know where the robot is and what the map around it looks like. So I'm just going to drive around the lab a little bit, and then we'll be able to see kind of what the lab looks like. And now that we're kind of done, again, you can see we have a map of the environment, we have a loop closure, and SLAM is essentially a key component in enabling robot autonomy. So a lot of the work that we're doing in kind of remote inspection, mission planning, all of those kind of things relies on the ability of the robot to know where it is and the structure of the map to actually do useful things. You know, nuclear decommissioning, those kind of things is what we're looking at. The handheld has its uses, but also if we can do this with a robot, obviously we don't have to send people into the same places. Sometimes it's easier to access places with humans, so the handheld device is useful, but other times we'd prefer to use a robot. So we have both options.
This is the one we saw in Bristol, wasn't it?
Yes.
On the front, we've got what we call a frontier device.
It's running the exact same mapping software, but we're just not running the autonomy part of the system right now.
What I'm going to show is the algorithm that is running inside the frontier and the main technique that is using it, which is called factor graph. So a factor graph is a way to solve this SLAM problem by modeling the unknowns as nodes. So we might have our position x1 and then position x2, position x3, and so on. And this is what we want to know, in addition to landmarks, which are basically points in the environment, which eventually will make up our map. So we can think of the landmarks as L1, L2, L3, and so on. And the measurements that come from camera or IMU or any other sensor create a relationship between these unknowns. The IMU might just tell us, okay, so between x1 and x2, your position should have incremented by this amount because your acceleration was this much over this period, therefore velocity and therefore position. And at the same time, you can have multiple IMU measurements, so you connect this. And from x1, you might just see also things from the camera, features in the environment, for instance, a corner that you can track over time. So this creates also some other relationships between our position and the landmark. And you can see the same landmarks over different times, so you can create these sort of relationships. And if you keep adding all of these constraints, then you have a strong idea of where you should have been and what was around you, because all of these relationships are merged into an optimization problem where the unknowns are exactly x1, x2, x3, and L1, L2, L3. And in this way, the algorithm will find the best solution that makes sense of all of this relationship together. And then the last bit comes to solve the SLAM problem. Imagine that we walked a very, very long way. So imagine I've made this chain very long. And at some point, we are at time x50. And in reality, we should be in x2 because we have kept track of all of the measurements we have collected so far. And so we have a map of them. And we close the loop by thinking, okay, I'm exactly in the same place as x2. So I can create a relationship between x2 and x50. In this way, all of the error we have accumulated up to x50 gets corrected, the map gets warped to match reality, and we have solved the SLAM problem. It's oversimplified if I say SLAM problem is solved. Many professors will become angry. Yeah, you have solved the SLAM problem in this specific situation. Yes, you did.
But not generally solved it.
No, yeah. So in practice, it's yet not solved because there are many problems related to noise in the sensors and inaccuracy in the calibration. So there are techniques to make this solution more robust, for instance. So if you have a SLAM system working, then you know where you are and what's around you, and also robots do know where they are and what's around them, so we can do autonomous things.
Jane Street is a research-driven trading firm with offices in New York, Hong Kong and London. Full of impossibly creative and clever people, they like to think the next star individuals that may be working for them could be watching this computer file video right now. That's why they're hoping you might peruse their website, including this section for internships. Are these the sorts of jobs that might launch your career? Check out Jane Street. There's a link in the video description. And our thanks to them for supporting this episode of Computer File.